really fast.
Yeah. And then Sam was sleeping on there, or snoring on there. And it's so loud, I was like,
There's some song I feel like you have the right to hit that.
yeah, I was about to wake him up and be like, stop snoring.
Dude, we went to the house. You took my spot, my blanket, and you were snoring. Yeah, I know when you were sleeping.
Is there anything in there? You gotta put that in. You have to eat it, skip it. And you have to finish both of them.
I finished one already.
No, there's like one more.
Surely this can.
You just eat the carton. Let's go, eat the carton.
I gave it to you guys.
He lost those. But like he had some close ones though, so that it wasn't like
I
bad.
think it could be okay if you actually finish the way you tried to do it.
If he just learned like gets good at one move, he'll be good. Like a duck under.
He is good at one move. Push ball. Whenever I wrestled with him, he did push ball every single time.
Oh, he didn't do that.
Jordan tried to throw every time he was hungry. Like all he was trying to do was throw.
It worked like 7 times.
Yeah, like now.
He was good though, like more than most people.
Yeah, like when he threw it was good.
He almost hit one in the
And then he over-rotated and got him.
I don't think he got pinned.
Yes, he did.
Well,
From
it was.
Slinger?
I don't know.
Yeah,
I just remember
he was winning the match, and then the guy came back because he let him
No,
try, and then the other guy got
Was that the one where like they both like run at the same time? And he almost hit it though.
I feel like
But
it
he
was,
didn't on the back end.
they was the heavyweights not to like go under. But I feel like he definitely did.
So he's not even heavyweight anymore.
220, same thing.
I don't know.
All right, I'll remind you guys, or I'll let you guys know about, in terms of these equations when, I feel like the ones that are really like logical in my head and I think most people is like, they get the idea of height versus times, you know, velocity versus time. Once we throw derivatives of interest rates in there, it's kind of confusing because if you're not, I mean, we understand height, we understand speed. I don't know that a ton of us really understand what it means, like the derivative of like your interest rates or like how much money you've saved. So totally understandable if you couldn't explain it. Like, so part C was like the tough part of this, then I would understand it. The first couple hopefully are okay. So they're telling us the amount in the account is A of T. So they're telling us to put T in for the first equation. So this is basically saying A of 10. So we're just substituting the 10 into this equation, which is an equation I know you guys have evaluated before. You know, exponential is hopefully not something that's too bad. So we're just putting 10 in there. And that's how you get, is it 911 or something? Yeah. Okay, so then, yeah, so that's just a matter of being able to put that in your calculator correctly. Then they say A prime of 10. And so, again, if you're not comfortable with that and like what that means, I wouldn't be too stressed about that. I definitely will stick to like the subjects that we're more comfortable with, like speed and height and that kind of thing. So then they just want you to put it into this one. And then, what does the answer mean? So again, what they're trying to get at there, I believe it's, so kind of talking about the amount it increases at that point. So again, if you struggled with that explanation, I'm totally okay with that. Like, we'll stick with mostly speed and height, and we're going to talk about one next level of that today. So then, number 7. All right. So they want the average velocity between 2 and 3 seconds. So we first have to find the velocity equation. So we put the 2 down in front, so 2t plus 3. find the average velocity between 2 and 3 seconds. So basically we're going to find the velocity at 2, the velocity at 3, and find the middle point of that. So like we'll do so at 2 seconds it's 7, at 3 seconds it's 9, so the average velocity between those two would be 8, and then we're talking about velocity, so meters per second. What's the instantaneous velocity? So that's talking about t is 6, so again s prime of 6, so that's going to be 12, so 15. And then the initial velocity is at time of 0. So you put in 0, so it ends up being 3. And then this last one, again, we've talked about, oh no, not that one. Oh, this one doesn't have it on here because I took that off a different, I think, right? It's missing that. Let me grab it.
Jerry, you excited? You nervous?
No. Well, I know I suck already, so.
I'm gonna try it. Is it home?
Yeah.
Wait, it is?
Yeah.
And then I can watch. It's on my own. I think, right?
5:50.
My bedtime
Tip.
is like 8:30. I leave at halftime when it's on one game.
Why?
Because I get tired.
Yeah.
If you watch me, like when I do like score around like right at halftime of the varsity game, I'm like, I yawn like every 5 minutes. I'm so tired. And it's not even like I go to bed that early, but like I just want to be like at home,
Yeah.
like on my couch at that time.
I feel like
I hit a wall.
I feel like they have like varsity events really late.
Yeah.
Like why do they have to make them like end at 9?
Girls softball.
Like why can't they just start like the JV at like?
Girls softball starts at 4 p.m. and then JV's after that game. For softball, our varsity is at 4.
That's good. Because then you can actually get to bed at least.
Yeah. I don't know if we will this year. I don't know.
Okay.
But then if we don't, then like 2 girls are getting cut.
So,
And half the team are playing.
and I don't think you need to know a ton about like racing to understand this question. Hopefully this makes sense. But so the diagram shows a part of a racetrack. The driver travels at top speed in the straight parts, but will slow down in the turns. Hopefully that seems obvious that you would not like, speed up for the turns. So what they want to say are, so which is a better description of a distance versus as a function of time? So they have time across the bottom and then distance up the side. So in terms of this, like we're talking about this guy going, he's going fast, and then he's going to slow down around the turn here. So in terms of our graphs, distance versus time should never be, you shouldn't be going negative in terms of distance, if that makes, like, so you shouldn't be going down at all because we're never like losing distance. So picture it, this is, I don't know, 5 feet, this is 10 feet. So like distance versus time, he'd be going up to 10 feet. At 10 feet, he's got to slow down. So the distance that he covers versus time is gonna like level off because he's gonna slow down through that turn. Then he's gonna speed up again. And then again, he's gonna turn, so he's gonna slow down. So understanding a distance versus time graph should never actually dip down negative. And so, because otherwise that means we've somehow gone back and like our distance has gotten smaller again, which it'll keep getting bigger because we keep moving forward. Now this graph though, it's flat at the start, it's constant, and this is speed or velocity. So constant, then the speed is going to go down because he's going to slow down through that turn. then he's going to accelerate again, it's going to go back up, then he's going to slow down again, then it's going to accelerate. So the difference in the graphs, and this is just kind of, again, kind of like dipping our toe in the water of like calculus and thinking about that, and actually like physics, these graphs that kind of all relate in that way. So just thinking through the problem, distance versus time versus a speed versus time, they will have different types of graphs. So we didn't really talk about that in particular, but hopefully that sounds a little more logical now. All right, so good news is today is not much different. So, I mean, I feel like the start of this chapter was rough, and then now it's been.
I don't even remember the start of this chapter.
The start of the chapter was when we were substituting. We did that h, the x plus h. Yeah, it was really long. Like, but this doesn't happen very often. The chapter gets like easier, but. And so today's gonna feel a lot like what we've been talking about already. We're just gonna add one more piece to this. And again, this reminds me a lot of like my high school physics class. This section, we talked a lot about this when I was in, physics was probably my favorite class in high school, even though I am a math teacher. I thought I was gonna be a physics major in college. I took physics and AP physics. Then I got to college and realized I did not like it as much as I thought. So physics major was not in the cards for me.
Oh, that's where you're supposed to write your name. Mom's probably in a different It'd be better if they, wait, I can just
Gonna name your
Where do
calculator?
you write your essays? Oh, okay. I wasn't sure if you were weird enough. I wasn't sure if you like started at the bottom and like up.
Why would I do that?
I don't know. How do you write your D's? You go like this.
Like that.
What did you do? Oh.
Okay. What are your weird letters?
B's?
Yeah. Who does that?
What is it?
Well, just like a 6. How do you distinguish between?
Because my sixes are more curved. Like they like come out.
What if it's not curved?
But it is.
What if you decided?
What other? You write other letters really good.
I don't know, you don't know how I like write my C's, I go.
Is V's and U's? That's what it is. They look exactly the same.
Yes. Who starts at the bottom when they write? He went at first T. He went up. Oh, ew.
And then you go across.
Yeah. He goes like.
It's
from the
more
bottom
efficient.
up.
Yeah.
You can write faster that way.
Because he's already at the bottom.
Because
Yes.
I feel like I'd be thinking too much about it.
The T is the cross on the T is closer to the top than the bottom.
That's how my search term works too.
Exactly. You
Wow, I
gotta
just go
think-
like this.
think
Do
smart
your
now.
V's and U's.
Well, you can't do that small.
Well, I need like a word.
All right. So our warm-up question is asking us to find the derivative of these. However, they both need a little bit of work before we start. You can't just find the derivative the way they are. You're going to have to FOIL first in order to find the derivative here. Mentioning my college physics class, the thing I remember most, well, there's a couple things, but I took college physics with one of my guy friends, and I looked over at one point during the exam, bless you, and he was sleeping during the exam. He said he took a nap during the exam because he had stayed up all like night studying, and he got so tired that Like it's like a 3-hour exam, so he like slept for a little bit and then like woke back up and finished his exam. I like looked over like he's sleeping. Like
I need stress if I don't have enough time.
oh my gosh, yeah, and like, cause that was like the time before cell phones was, or like, I mean, you couldn't have like woke yourself up. I don't remember how he. Then I was stressed because I was worried about him like not waking up for the rest of the test.
What college did you go to?
University of Minnesota.
Oh.
Remember we talked about that, Brock Lesnar.
Oh yeah.
I had the cutest little like physics professor. He was so old, but he used to do things that like we thought he was gonna kill himself during class. He'd do experiments and like we were like, he's gonna die today. Like this is gonna be the day to watch our physics professor die. Like he'd fall off the top of like the lecture table, like and we'd all be like the guy in the front row would always go check on him. He was the cutest old man.
Yeah, he's so cute when he does something.
Right, well, right, because he would do these like he stood on the top of the lecture table, like the big kind of like lab table, and he wanted to show us that the fire extinguisher worked before he did the rest of his experiments. So he blew the fire extinguisher in us, and he fell off the back of the table. He was wearing like an old school Gopher football helmet when that happened. So he was the cutest old man. Like, and
What
then
did he say when he like got up?
he was like, "I'm done," and we're all like, "Oh my god!" And then still that same day, he got on this little cart and blew he had the fire extinguisher blow him across the room, like with the cart, and he flew into the wall, like with it, and we were all.
They're that powerful?
He had, I don't know, the cart.
You should do it. You
Yeah.
should go get him.
Poor guy. So. That was like 25 years ago now, so like it's been a while. But maybe not quite 25, but. I'll never forget him. I'm sure he's not alive anymore, but he was so cute. So we have to find the derivative of each of these, but again, we had a FOIL first in order to do that. So this one's going to be 20x plus 6, and then this one is going to be 32x minus 24. And remember that 9 just kind of goes away. And then just watching for the difference when they're asking for putting -4 into the original function or into the derivative. Those like slight differences, obviously they have different outcomes. So just getting comfortable with that. I think you guys are, but I figured I'd just throw that into another form. Actually, substituting the value is hard. It's tougher to put in the original rather than the derivative. Is this 136 here? Shows that. Yeah. I believe this one should be 25 here. What you guys got? Yeah. All right. So again, we're going to talk more about like that velocity, like the fact that the velocity is the derivative of our height function. We're going to add one more layer to that. So we're going to talk about acceleration and deceleration. Now we're not getting a ton into that concept, but acceleration is like how quickly the speed increases. Like so, it's the next level of velocity. So velocity and acceleration are not the same thing. So it's adding like another layer to that. So. So the units we use is like distance over time. So like if it's meters per second, feet per second, miles per hour, that's a measurement we're comfortable with. And so acceleration is the change in velocity. So how quickly the velocity, or how much the velocity is changing. So you're going from 60 miles per hour to 80 miles per hour, that's an acceleration. So it's the change in acceleration, or change in velocity. And then deceleration is the change but a decrease in velocity. So you're slowing down. I think these are a little bit tougher to wrap our mind completely around because we don't talk about that as a measurement very often. Like it's not like your car is telling you what your acceleration rate is. Like it tells you your speed, like that's, but how quickly you're changing that. So what this adds to this is just adds another layer. So if I'm talking about miles per hour, it's actually miles per hour squared because it's per hour per hour. So it's like we're finding the velocity over time. So whatever the rate is, we're basically just gonna, so if it's meters per second, it's gonna be meters per second squared. Whatever that unit is, like the time unit's gonna be squared. And how this relates to our original height function. So velocity is the derivative. Acceleration is the second derivative. So we're going to take that again. We're going to do one more derivative. And that sounds really tough, but it's the same process. Like it's not like it's, yeah.
So is acceleration going to be like really easy?
Yeah.
Like, pretty quick?
Yeah, it's going to be pretty, yeah, because yeah, you realize now that each derivative makes our equation a little more simple. That last one's going to be even more so. Most of the time, the variable's taken completely out of it, and the ones we're going to talk about are a lot of them. I threw one in here that was not like that, but are a couple in there. So, again, this shouldn't take us very long. We'll kind of get through these. There's only like 3 examples, but it's not because they're really long. It's just because there's only so many examples you can do like this. So, if they give us, this is our function here, the height in meters of an object at time t. I don't know why they use s, so it's like h of t, same idea. So the velocity function, again, is the first derivative. Now there is a decimal in there, so don't let that throw you off. Nothing tougher about that other than that you have to grab your calculator for that. That's just 9.8, right? Grab my calculator, realized I didn't probably need it. So our velocity function. The initial velocity, remember, is what? What is t at that time? 0. So when t is 0, so in this case, now this is one of the places that we have to be really careful about it, is just want to make sure our units make sense. So like what units are we talking about? Initial velocity 15, it's 15 meters per second, right? Find the height of the object at 6 seconds. Where am I putting that in? The original. So that's talking about the height. And in this case, again, they use S for whatever reason, but the height. So I'm putting that into our original function. It's weird. Right, is it negative?
That's what
I don't know exactly what the situation is, so I don't know why that would be negative. But anyway, maybe it's underground. I don't know.
Gravity.
So,
It's falling outwards.
find the acceleration function. So now we're finding the second derivative. So what that means then is we're taking this and we're doing double prime here. So the 15 cancels, so it's just negative 9.8. What is that? What do you think negative 9.8 means? Why do you think it's negative?
That's how much faster we go.
That-
That's how much slower.
There we go. How much slower we go. So that's how much we're slowing down. So this is slowing down. And that's going to be 9.8 meters per second squared is the way we write that. So this is slowing down. So that negative just means it's deceleration actually.
I have a question.
Yeah.
So does that mean at 1 second it'll be 9.8 less than 15? Like the velocity?
Does that work that same way? I would think so because that's our rate. Yeah, so yeah, like from 1 second to the next it would go. Because technically this is a linear function, so that like that means it'd be going downhill. It'd be going down 9.8 every single time, yeah. So yeah, it gets that much slower each second as you go along. Right before it hits the ground, that's kind of a rough question, isn't it? Letter F. So you need to figure out when it's going to hit 0, right? Yeah, let's get that one. All right. Because that's a rough, we have to do quadratic formula for that, don't we? We can't factor. Yeah, that'd be, let's not do that. Just kidding. Flip the page over. I'm going to upload this though.